Okay, this is problem 123 at the end of chapter 1. In this problem, it's an energy balance, and we're looking at a solar collector, okay, that is getting an intensity of 300 BTU per feet squared per hour. And it's a 4 by 8 foot solar collector, and the water that's circulating through it at 1 gallon per minute is getting heated while exposed to that light intensity. Okay, so the collector's not 100% efficient, so I've redrawn it here. Okay, it's not 100% efficient. 50% of the sunlight is actually captured and heats the water. So what would be the temperature rise of the water as it leaves the collector? Okay, so going back to what we learned in class, we have our rate of change of stored energy. Remember, that was delta U, that internal energy, and it's a rate, so I've put a dot on top of that, equals the mass rate times the specific heat capacity times the change in temperature. And remember, because this is energy per time, it's also power, okay? And also we are given this term intensity, and intensity is the power divided by the area. All right, and that's why it's in these units of BTU per hour per foot squared. Okay, so it's the power divided by the area. Okay, so then we can actually back out of that. We can get the power, and I've just done that here just so that we have it. The power is going to end up being the intensity times the area, 300 times 32, or 9,600 BTUs per hour, and our area units cancel out, right? That's important. Okay, so we have BTU per hour. Okay, and then also remember we said that this mass flow rate, just like in our mass balance, all of those balanced terms are mass rates, so that mass rate equals the actual flow rate of water into the collector times the density of water. Okay, so now we know that our rate of change of stored energy, which is actually only 50% of the power that was input from the sun, equals this mass flow rate, QW rho W, times specific heat capacity of water times delta T. So this is what we're looking for, is this delta T term. Okay, so solving for delta T is 0.5 times the power, which we said is 9,600 BTUs per hour, divided by the flow rate in. Flipped these. This is the specific heat capacity, and this is the density of water from table 1.4. Okay, and doing that gives us a final change in temperature of 9.6 degrees Fahrenheit, and that's how much the water in the collector has changed in temperature.